oscilloscope testing this circuit, which is working okay, and everything seems to be good, but the master clock seems to be a little too slow. And when I make another master clock, it makes it work, but it makes it go faster when the two are combined. So here I am looking at the reset signal. The reset signal is coming out of the TLC 555 timer set in monostable mode, which is right there in the middle of the screen. That timer is set to deliver a 340 microsecond pulse that latches everything and resets the counters for the chips. Now, for the entire count, so that it will reset after all of the LEDs are lit, all of the bits are sent, which in this case for all these LEDs there are 144 of them. So times 24 bits of value for each one, that should total 3,456. And that signal, if it's running at 800 kilohertz, should be at 231 hertz. And if I look at this reset signal, which is exactly, each division is 100 microseconds. So this reset signal is exactly 1, 2, 3 and a third, so about the right length. So the reset signal is being sent, but it's being sent at about triple the speed, which means that when I plug my LEDs in and I mess with the input signal, it will reset and latch about a third of these LEDs, which makes sense based on the frequency of the input signal. So there's a problem with my master clock. That's good for the oscilloscope. And you can see these signals are coming out regularly. And it's working well for a third of the LED strip because it's latching too quickly. And while there's still fine control, when I test it with this little voltage controlled oscillator, it's not quite right. So I need to make a more reliable master clock. By the way, for anybody who wants to buy an oscilloscope, this is my first ever oscilloscope, so I bought the cheapest model out there, which is the FNIRSI 1014D. Now, I'm not being paid by anyone, but I bought it because it was the cheapest entry-level scope out there. Every other one is like really, really expensive. And I know some people have poo-pooed this, especially the fancy people out there who are used to using big, expensive digital oscilloscopes, but this thing is money. And it does everything I need it to do. And when I capture these signals, it does everything that a regular oscilloscope does. So my next step is to try to make a better clock based on the current state of affairs that I have going on here. And I think that once I have a more stable clock, if I could make this signal happen every 231 times a second, that will slow it down to the point where I can actually light up the entire LED strip and have a more reliable source here. So if I take this probe and I put it to the clock signal here, which is the combined clocks, let me zoom in on this. Let me get a single capture. Do it again. You see I have two clocks running at the same time. And you know, it's set, it's reading it as 381 kilohertz, which is not really true. But you can see the fact that there's two clocks superimposed upon one another here, and that I think is what's driving. See the signal, it jumps to 655 kilohertz, depends on where it's sampled, and you could see the clock reset signal coming in every now and again. Let me see if I could actually get it to capture. There it goes. Let me change the resolution here so I can read that in. And you can see these are all the clock signals superimposed, so it becomes a very dirty signal. But here you go, there is a reset signal to the clock that comes every now and again, and this is when the full count is completed, and that's happening way faster than it, way more frequently than it should be happening, because these two clocks, when added to each other, end up producing much faster frequency. And while this is still getting activated and the LED strip is working, only a small portion of the LED strip is lighting up because it's latching prematurely. So in any case, I am going to work on a better clock. But anyway, thanks for watching.